This has one curvature, and this has two, but there's no way to put three because the indices don't match. Okay? So this is all there is. And of these three, the Einstein-Hilbert Lagrangian is this one. And you can guess it's this one because it's linear in the curvature. It doesn't have curvature squared. This doesn't have curvature, so it's not that one. This has curvature squared, so it's this one. And let me see how much time we have.
Sorry, what's the problem with curvature square?
There is no problem with curvature squared, but the Einstein-Hilbert Lagrangian doesn't have curvature squared. We will talk about it next class. So in the time we got, let me show you that this indeed is the Einstein-Hilbert Lagrangian. I'm going to write down all the indices of these forms explicitly. With all the differentials. So R is a two form, so mu nu. This is a one form, so altogether it's a four form. Now this is 4 dimensions, and this, since this is a wedge product, this is completely antisymmetric in all the indices. And so you have something that is completely antisymmetric in 4 indices in 4 dimensions. So it has to be a multiple of the Leibniz tensor. And so what we get there times dx0, dx1, dx2, dx3. And this is what I call d4dx. So this thing here is this. Next, I'm going to use the field bind to change these two indices here, this AB, to kappa lambda, or rho sigma, or kappa lambda square. Kappa, lambda, AB. So I use the field bind to change basis, to change this index from the orthonormal basis to the coordinate basis. And the same with B. And now, if you take this one here, and all these guys there, you have epsilon ABCB times this field by 4 times ABCB. This is completely antisymmetric. So if you make the computation, what you get is the determinant of this matrix. times an epsilon, a little beta, but in the kappa, lambda, rho, sigma indices. So you get this. What I'm doing here is for any this is a way to compute the determinant. You have a 4 times 4 matrix, and you contract all the upper indices with an epsilon tensor, you get the determinant times the epsilon in the lower indices. So this is what I'm doing here. And when you have 2 epsilons multiplied together, this is called a generalized Kronecker delta. Have you met this generalized Kronecker delta before? Yes? It's completely antisymmetric in all the indices, in all the upper indices, in all the lower indices. And it satisfies a lot of identities. For instance, here you have rho sigma, rho sigma. So you can show, I will not do it, but you can show that this is 2 times so this these 2 indices are antisymmetric because they are indices of a differential form, and when contracted with this Kronecker delta, they give you 2 times and this is the Ricci scale. What is the determinant of the field line? We started with this equation. If we take the determinant here, this will give us the determinant of the field line, determinant of eta, determinant of the field bind and determinant of G mu. Now this is the same as this. It's determinant of the field bind squared. What's the determinant of eta AB? It's -1. If you multiply the elements in the diagonal, minus plus plus plus, it's -1. And this is called G. This G is the one that appears here, the determinant of the metric. And so if you that's where it is. So that's my proof. I know it went a bit fast, but this kind of manipulations are very typical. It's a thing you do all the time here, and you get used to it. Okay. The product of four differentials is the epsilon times d4x. Then you change these indices from the orthonormal basis back into the coordinate basis. You use this times this, gives you the determinant. Then you multiply two epsilons to give a delta. You use the contraction identities for the delta. And finally, you realize that the determinant of the field bind width is the square root of -g. And this finishes it. So actually, this is the Einstein-Hilbert Lagrangian. So you can do general relativity in this formalism, but you can also do different things. Or you can include this one, or you can include this one, and you can include the other ones that we wrote down. All those are, in principle, valid Lagrangians, and they give you generalized theories of gravity, theories that share all the principles of general relativity, but they are different in the detail. They have different Lagrangian and they have different field equations. Questions, please?
These different field equations mean probably different physics, no?
Different physics, yes.
So what Einstein said to Cartan, said?
Cartan.
Why bother? Why bother if the Einstein-Hilbert is?
That's a good question, actually. In 4 dimensions, we will see in the next class that actually, well, I can tell you now, this guy here, this gives you the cosmological constant. And this guy here doesn't contribute to the field equations. We will see why. But you can, if you add it, it doesn't contribute anything.
But what do you mean gives you the cosmological constant?
If you include this Lagrangian, for example, you take alpha 0 times L0 plus alpha 1 times L1, then what you find is the Einstein-Hilbert Lagrangian plus a cosmological constant. So it's nothing new in this sense. And this one here, this gives you a contribution in the Lagrangian. But if you compute the field equations, it doesn't contribute anything, it gives 0. We will see why.
It's like a ghost.
No, it's not a ghost, but it's a total derivative. It's a topological invariant.
But so the change in the field equations is all in the
with a cosmological constant. It's nothing new. And L2 doesn't include. So in 4 dimensions, this gives you nothing new. But we're not sure space-time has 4 dimensions. Maybe it has more. And we will see in the next class that if you go to higher dimensions, then you do get corrections. For instance, if you go to 5 dimensions, then epsilon has A, B, C, D, E. Has 5 indices. So you get R, and another field bind, a 5 form. And this Lagrangian gives you modified field equations. It's called the Einstein-Gauss-Bonnet theory. And this is a viable theory in 5 dimensions. It's hard to argue why it shouldn't include this term. And if you go to, say, 11 dimensions, there are several other Lagrangians you can include. So you're not sure that in higher dimensions, gravity has to be equal to general relativity. It could be something different. And it's not too crazy. It's very conservative actually, because it's based on the same principles, the same differential geometry. More questions?
What about the other possible Lagrangians, including torsion?
Oh, well, those include torsion. all the others that we wrote down here include torsion. And so people tend to cast them in a way because they include torsion.
Yeah.
But actually, they may be necessary. Because if you try to build a supergravity theory in this spirit, then to supersymmetrize these Lagrangians, you're going to need to include the torsion versions. You cannot supersymmetrize Lovelock alone. You have to include torsion.
But what's the connection between the supersymmetrized and torsion? Why do you need to?
Because you need gauge invariance.
Okay.
So to ensure the invariance, you need to have those new terms.
Yes.
So it may be necessary to even go beyond Lovelock alone. Because Lovelock is only this.
Yes.
It's only this
Only
epsilon, field bind, and curvature. Nothing else. But there are more things.
Just a curiosity. In earlier classes, we're talking about gravity quantum loop versus string, and for example, Professor Aula is a diplomat. So, but do you like quantum loop or? I think that nobody here works with it. Don't worry.
Mas alguém aqui no CDPF trabalha com isso?
Não.
Eu quase disse alguém aqui no Brasil trabalha.
Then?
Tem.
No, I never studied really in detail quantum gravity. I know only a bit, but what I know, I don't really like it, but it's just a matter of taste. In the end, what's important is not whether you like it or not, it's whether it matches nature, it matches the experiment. I don't like string theory very much either, but but that's my opinion. Who cares?
In the next class, we are going to derive the field solutions.
We're going to look at the field equations.
Field equations.
And show that these field equations have as a solution that torsion is equal to 0, for instance.
Okay.
That's one solution. And we're going to look at the Lovelock theory more in general, including in higher dimensions. And then I want to talk a bit about Chern-Simons gravity.
About what?
Chern-Simons gravity.
Chern-Simons.
Because if you see, here you have three Lagranges, and the easiest thing you can do is build a linear combination of that. So a constant times L0 plus constant times L1. So it's like a polynomial. You know, this is order 0, order 1, order 2. And so the general Lovelock Lagrangian is a polynomial with several terms. But there are constants in between. Like every term has a different constant. So there is a lot of arbitrariness in the Lagrangian. And people don't like to have arbitrary constants because they can be anything. So the less constants you have, the better. And so I'm going to talk a bit about how you choose these constants, and also how you can think of gravity as really a gauge theory. Because here the omega is a connection for the Lorentz group. It helps you to define a covariant derivative, it defines curvature, etc. But the field band is something else. The field band is not a connection, the field band is a vector. So you have a theory which has a connection and a vector. And you can do a little bit better than that. You can have a theory with only a connection, like a pure gauge theory. Like Yang-Mills theory without matter, for instance. And this is connected with the question of the coefficients. So I want to go.
We're not going to couple the matter fields.
No, we're not going to cover the matter fields. No, that would take us very far away.
Yes.
And when do we couple things to gravity?
Well, this is pure gravity. Because gravity and nothing else.
In quantum loop, never.
Of course, you can have a thin energy momentum tensor in the right hand side of the equations. And then you can do anything. You can see, you can do for cosmology, for instance. You can put what cosmologists do. They put dust and radiation and this different kind of thin and look for the cosmology of that.
Okay.
So there's many things you can do.
Mhm.
Okay, guys, thank you for your patience.
Thank you for fantastic.
And see you next Friday.
Okay.